Let's now take a look at an ideal EDA integrated workflow. Once again, we'd like to start in a data managed workflow, which means going to TeamCenter to check out our design. From Expedition, we can open TeamCenter and search for our SC100 PCB. We can see that the data type is a PCB layout in the properties, and we can go ahead and check out the design. All stages of the PCB design process is TeamCenter managed, from the schematic diagrams showing the component connections to the layout and routing, which physically places the components on the board. This PCB is fully placed and routed, and we can see the 2D placement here. The 3D viewer in Expedition is useful for visualizing the fully populated PCB. This 3D functionality can be dynamically linked to NX using the ECAD-MCAD collaborator, which allows for co-design with the NCAD team, so changes are dynamically updated bidirectionally. Let's now export the PCB in CCZ format, so the detailed traces and board detail can be used for thermal simulation. Back in TeamCenter, we can see the EDA Expedition board design is currently checked out and being actively worked on. In NX, let's start with a blank assembly and go into the Flow EFD simulation mode. On the Flow Analysis tab, we open EDA Import to start the Flow EDA bridge. The CCZ file is imported, and we can see the Expedition design ready for preparation. We can click through the layers to ensure we're working with the fully populated and routed board. If there are layers we don't want to include, we can open the StackUp editor and remove layers such as the top and bottom solder masks. The StackUp editor is useful for interrogating the layer thicknesses and percentage coverage of copper also. Let's now use the filtering command to remove the components we're not interested in. Filtering on reference designator naming convention allows us to quickly remove connectors and inductors which already have accurate 3D models associated with them in NX. This leaves just the active components, and we can check the top and bottom of the board to confirm. Next, we'll import a thermal list, which is a CSV table of data we want to overlay onto the board. This is useful for boards with a lot of components needing thermal inputs. Data such as the IC model type, the thermal resistances, power, and whether they're filtered or not can be defined. We can see the thermal power and modeling type applied in the component tree by clicking through the parts. The main processor for this board is an FPGA, which is the most thermally critical component and needs special treatment. Flow EFD includes a tool called the Package Creator for generating thermal models of components. It's a wizard-driven tool to define all of the internal structure of an IC package. Parts such as the die, encapsulant, solder balls, and substrate can be parametrically defined. We can see the solder ball pattern on the underside, which will be a critical heat flow path into the PCB. The component can be stored in the FlowEFD library and used to replace the simple block representation from the CCZ file. Zooming in, we can see that the FPGA is correctly aligned to the BGA pads on the top PCB layer. The final step is to change the PCB modeling level to Smart PCB. This is an advanced Flow EFD PCB modeling functionality which creates a thermal resistor network for the conduction paths within the board. Rather than modeling the micron scale geometry explicitly, the Smart PCB translates the conductor and dielectric materials into a resistor matrix which has a much lower computational overhead. Everything we've seen so far in the Flow EDA bridge serves to augment the Expedition PCB export file with inputs needed for an accurate thermal simulation. Once the assembly is transferred, the PCB looks bare, but we actually have all the heat-generating components and PCB modeled in high detail. The Flow EFD project is automatically created, and we can see all the input settings in the thermal simulation tree. Materials, 2 resistor components, and the Smart PCB can be visualized on the screen. We can show the Smart PCB colored by thermal conductivity to confirm the detailed design has been captured. Switching to an internal PCB trace layer, we can see high copper content, which is good for spreading heat. The PCB through vias and mounting holes are also captured for an accurate thermal simulation. The final step is to place our prepared PCB into the main assembly and combine it into our detailed 3D model. We can once again show the Smart PCB on screen to confirm everything is in the correct location and orientation. Staying integrated with TeamCenter and NX ensures accurate EDA data capture and usage with a streamlined, traceable thermal workflow.